When examining the neurobiology of depression, one important area to focus on is neurocircuitry of the brain so that we can understand depression from that lens. In this lecture, we're going to be looking at two specific parts of neurocircuitry, primarily the cortical area and the subcortical area. And more specifically, when we talk about cortical areas, we are referring to the prefrontal cortex, or the PFC, and the different parts of the cingulate cortex, such as the subgenual cingulate cortex and the anterior cingulate cortex. When we are speaking of the limbic system, that's going to encompass things such as the amygdala, which we think of as the seat of emotion, such as anger and fear. The hippocampus, which has been associated with memory, you might remember from Psych 101, but it's also been associated with our experience of stress, how we respond to stress. So the hippocampus is very much involved in that autonomic stress response. And then the nucleus accumbens, which that tends to be the seat of a lot of our dopamine tracks eventually. So again, just a quick reminder, we think of the cortical areas, the prefrontal cortex, as inhibiting a lot of our subcortical activity. So subcortical activity in the limbic system kind of organically occurs, and the prefrontal cortex helps keep that in check, helps inhibit some of those responses, such that the cortical areas, that's where a lot of our cognitive processing comes from, our ability to delay gratification, our ability to think through the consequences and then make an appropriate decision. That's going to be that explicit response selection, again, where you're making a very thoughtful decision. It's also how we cognitively process emotion. Again, the amygdala and the subcortical areas, that's going to be our instinctual experience of emotion, that fear, that anger, and then the prefrontal cortex helps us put words to our emotions, right? Helps us to kind of process that at a more cognitive level. I feel sad because of ... right? The limbic system, again, including the amygdala, hippocampus, nucleus accumbens, and some other things, this is going to be representative of those autonomic responses to stress, our autonomic experience of emotion. This is where we assign emotions as positive or negative. We don't get so thoughtful about it as we do at the prefrontal cortex level, but you are assigning a valence to it. Is this a good feeling or is this a bad feeling? But it is going to be our natural implicit response to emotion. So what's generally, again, thought is that the prefrontal cortex and the cortical areas typically inhibit the limbic system. So that's just a quick review of those parts of the brain. Now let's look at how they are related. Before we do that, though, I am going to show you just a quick graph or image so you can just be reminded of kind of where these parts of the brain are, and then we'll come back to this image in a minute. So if you're looking at the image here, you can see the prefrontal cortex is right here, and we typically see decreased volume in the prefrontal cortex. The subgenual cingulate is kind of in this area, so it's kind of in that middle area. Oftentimes, the cingulate cortex, the anterior cingulate cortex, and the subgenual cingulate cortex, it's almost thought of as the transportation byway between the cortical areas and the subcortical areas. It's more associated with cortical areas, but it's thought of that communication channel because it does just have a strong connectivity between the cortical area and the subcortical area. And then of course down in here is going to be our subcortical areas, including the amygdala, the hippocampus, and the hypothalamus, and the nucleus accumbens, right? So that was just a quick review of where those parts of the brain are. But let's come back and look at how this neurocircuitry impacts depression. In understanding how the neurocircuitry works in terms of depression and understanding the etiology of depression, we have two primary theories. One is that depression results when there is a bottom-up functional issue, that there is a lot of hyperactivity in the limbic system. Again, the amygdala, the hippocampus, there's a lot of hyperactivity there such that the cortical areas are not able to inhibit that activity. It kind of gets behind the eight ball because there's just too much activity coming from the limbic system to help manage that at the prefrontal cortex area or the cortical area. From a top-down perspective, this is where there's believed to be hypoactivity of the cortex, and it can't regulate normal activity of the limbic system. So the bottom-up theory is that there's too much activity, hyperactivity of the limbic system that overwhelms a likely normal functioning cortical area or prefrontal cortex. The top-down theory is that the cortical areas are hypoactive and can't inhibit normal limbic activity. It could be a connectivity issue as well. So if you think back to what I just mentioned, how the cingulate cortex serves as that kind of connection between the limbic system and the prefrontal cortex. Well, if that connectivity is limited, then there are some communication issues there, and that's also going to be considered a top-down functional issue. In addition to functional issues, there could be volume reduction. So again, and I'll show you the graph in a minute. Well, I'll just go ahead and show it to you now. When we talk about volume reductions in depression, we typically see reduction of volume of the prefrontal cortex. We also see volume reductions in the amygdala and hippocampus. And you might think, well, if it's all reduced, where's that hyperactivity coming from? What we see with the amygdala and the hippocampus is that the volumes of that part of the brain may not have anything to do with activity. In fact, you'll see here that we see decreased amygdala volumes, but increased amygdala activity. The decreased volumes have been associated with perhaps cortisol damage, meaning that when you experience a lot of stress, because that is the part of the brain that experiences stress and manages stress, it causes some cell death and cortical shrinking in that area, or subcortical shrinking. One thing I want to highlight, I've got the red circle around it, is when we talk about the cingulate cortex, there's been some mixed research showing what happens with the activity. Again, some research shows that there's increased activity there. Some other research shows that there's decreased activity there. Some of the research that shows there's increased activity is based on the idea that when we do deep brain stimulation with depressed patients, we're reducing activity in the cingulate cortex and they improve, which would suggest that they had increased activity to begin with. So although we see a lot of reductions in parts of the brain like prefrontal cortex, cingulate cortex, amygdala, and hippocampus, some areas may have increased activity, some areas may have decreased activity, and some it's a mixed bag in terms of what it's going to be.